There is a planet in our galaxy where the oceans boil. Not metaphorically, not eventually, right now. Every second, the surface of this world absorbs more radiation than 1,000 nuclear explosions. The star it orbits sits so close that 1 year on this planet lasts just 33 hours. 33 hours. That is how long it takes to circle a sun that should have vaporized it eons ago. And yet, if oceans truly exist there, they have somehow survived where they should not. How is that possible? How can water survive where fire rules everything? The answer changes everything we thought we knew about where life can exist. The year is 2015. A team of astronomers at the Harvard-Smithsonian Center for Astrophysics is analyzing data from the Hubble Space Telescope. They are looking at a star system called K2-18, about 120 light-years from Earth. A red dwarf, small and cool by stellar standards. The kind of star that burns for trillions of years. They already know there is a planet there, K2-18b, discovered months earlier by a different telescope. A super-Earth, they call it. Bigger than our world, smaller than Neptune. Orbiting in what astronomers call the habitable zone. But habitable does not mean inhabited. It does not even mean survivable. The team is not looking for life. They are looking for something more fundamental. They want to know what this planet is made of. Rock, gas, ice. So they point Hubble at the star and wait for the planet to cross in front of it. When it does, some of the starlight passes through the planet's atmosphere. And in that light, encoded like a message in a bottle, is the chemical signature of whatever gases surround this distant world. What they find stops them cold. Water vapor. Not a trace, not a hint. Water everywhere. But here's the part that does not make sense. This planet should not be wet. It should be a desert, a burnt husk, because K2-18b does not orbit at a safe distance like Earth does. It sits so close to its star that the radiation should have stripped its atmosphere away millions of years ago. Imagine standing on a beach as a tsunami approaches. But instead of water, it is light, pure, unfiltered stellar radiation crashing into you every second of every day. That is what this planet endures. And somehow, against every model, against every prediction, the oceans survive. How? Let's start with what we thought we knew about planets and water. Water is fragile. At least, the liquid kind is. Too cold, and it freezes solid. Too hot, and it boils away into space. The range where liquid water can exist is narrow, impossibly narrow on a cosmic scale. Earth sits in that range by accident, or by design, depending on who you ask. We orbit at exactly the right distance. Our sun is exactly the right size. Our atmosphere is exactly thick enough to trap warmth, but not too much. Change any one of these variables, and the oceans vanish. Move Earth 10% closer to the sun, and we become Venus. A hell world, where the surface temperature melts lead. Move us 10% farther, and we become Mars. Frozen, barren, dead. This is the habitable zone, the Goldilocks region. Not too hot, not too cold, but just right. And for decades, astronomers believed this was the only place life could exist. The only place water could pool on a surface and stay there long enough for chemistry to become biology. But K2-18b breaks that rule, because K2-18b isn't in the safe zone. Not really. Yes, it orbits a cool red dwarf. Yes, the star is smaller and dimmer than our Sunday, but the planet huddles so close that the radiation is relentless. Imagine orbiting a campfire instead of the Sunday. The campfire is cooler, sure, but if you're standing 2 feet away, you still burn. That's K2-18b. The star blasts it with ultraviolet light. High-energy particles slam into the upper atmosphere every second. This kind of bombardment should rip molecules apart. Water molecules, H2O, are especially vulnerable. The radiation splits them into hydrogen and oxygen. The hydrogen, being lighter, escapes into space. The oxygen either escapes to or reacts with the surface. Over millions of years, the planet should dry out completely. This is what happened to Venus. This is what happened to Mars. So why not K2-18b? Scientists considered the obvious answers first. Maybe volcanoes replenish the water. Maybe comets constantly deliver fresh ice. But the math doesn't work. You'd need a comet impact every few hours. Volcanic eruptions that would tear the world apart. That's not it. The real answer hides deeper. Under pressure, no human could survive. Maybe the planet's massive gravity holds the atmosphere so tight that radiation cannot destroy it. This is closer to the truth, but it still does not explain what they found next. Because in 2019, they pointed Hubble at K2-18b again. This time, the spectroscopy data was clearer and more detailed. In that data, they found possible traces of something that should not be there: methane and possibly dimethyl sulfide. Let me explain why this matters. Methane on Earth is produced by two things: volcanoes and life. Dimethyl sulfide is even more specific. On Earth, it is almost exclusively produced by biological processes. Phytoplankton in the oceans release it. Now, finding methane alone would not be shocking. Methane exists on lifeless worlds, like Titan. But finding methane and water vapor together, in an atmosphere that should not exist, on a planet that is being roasted alive, that is when the mystery becomes something else. That is when it becomes a paradox. Here is what we now think is happening on K2-18b. But first, let me give you a different image. Imagine a pressure cooker. You fill it with water, seal it, and place it on a stove. The water heats up. It wants to boil. But the lid keeps the pressure high, and high pressure raises the boiling point. So the water gets hotter and hotter, far beyond 100 degrees Celsius. But it does not boil. It stays liquid. That is, Earth's oceans under extreme pressure at the bottom of the Mariana Trench. Superheated water, liquid despite temperatures that would turn surface water to steam. Now scale that up. K2-18b is roughly 8 times the mass of Earth. That mass creates crushing gravity. And that gravity holds onto an atmosphere so thick, so oppressively dense, that the pressure at the surface might be dozens or even hundreds of times greater than Earth's. Under that pressure, water can remain liquid at temperatures far exceeding its normal boiling point. So the oceans on K2-18b are not boiling away. They are trapped, compressed, superheated but stable. The fire does not destroy the water. It coexists with it. But that is not the twist. The twist is that this kind of planet should not be rare. It should be everywhere. And here is where it breaks our old map of worlds. For most of human history, we believed planets came in a few standard sizes. Rocky worlds like Earth and Mars. Gas giants like Jupiter and Saturn. Ice giants like Uranus and Neptune. That was it. That was the menu. Then we started finding exoplanets, thousands of them. We discovered a category that does not exist in our solar system: super-Earths. Planets bigger than Earth but smaller than Neptune. They are the most common type of planet in the galaxy. We see them everywhere, orbiting almost every star we look at. But we do not have one in our solar system, so we did not know what they would be like. Some are rocky, some are gassy. Some, like K2-18b, are something in between. They are ocean worlds, Hycean planets, scientists call them, a portmanteau of hydrogen and ocean. These planets have thick hydrogen atmospheres, like gas giants. But underneath, there is a surface. On that surface, under crushing pressure, liquid water oceans exist. Imagine a world where the atmosphere is so heavy that it presses down on the ocean with the weight of a mountain, where the sky is not blue but a murky, turbulent haze of hydrogen, methane, and water vapor, where the sun never fully rises because the atmosphere is too thick, scattering all light into a dim, eternal twilight. In those oceans, under pressures that would crush a human instantly, in temperatures that would cook you alive, chemistry happens, molecules interact, organic compounds form, maybe even life. But here is the real question, the one that keeps astronomers awake at night. If K2-18b has liquid water, if it has organic molecules, if it has conditions where chemistry can become complex, does that mean it has life? We do not know. We cannot know. Not yet. But the possibility is staggering. For decades, we've been searching for Earth 2.0, a planet just like ours, same size, same distance from its star, same atmosphere. We assumed life required an exact replica. But K2-18b suggests something different. It suggests life does not need our conditions. It just needs water, energy, and time. If that is true, if ocean worlds like K2-18b can harbor life, then the number of habitable planets in the galaxy is not in the thousands, it is in the billions. Let's talk about what it would be like to visit K2-18b. You approach in a spacecraft. From a distance, the planet looks blue. Not Earth blue, but a deeper, darker blue. The kind of blue you see in the deep ocean where sunlight barely reaches. As you descend, the atmosphere grows thicker, denser. The spacecraft shakes as it pushes through layers of hydrogen and helium. The temperature climbs, 100 degrees, 200 degrees, 500 degrees, but you do not burn, not yet, because the heat is balanced by the pressure. The molecules are packed so tightly that they cannot move fast enough to burn you. You break through the lowest cloud layer. Below, an ocean, vast, endless. But this ocean does not shimmer like Earth's. It does not reflect the sky, because the sky here is not blue. It is a dull, bruised purple, thick with haze. You touch down on the surface, or rather, you sink, because there is no surface, no land, no continents, just water. Water stretching in every direction, curving over the horizon. The ocean is hot, hotter than boiling, but it does not bubble or churn. The pressure keeps it eerily still, flat, heavy. You deploy a submersible. It descends 10 meters, 100 meters, 1,000 meters. And down there, in the crushing darkness, you start to see things, vents, cracks in the ocean floor where superheated water erupts, carrying minerals and gases from the planet's interior, just like the hydrothermal vents on Earth, the ones where life first began. Around those vents, chemistry happens. Organic molecules form, amino acids, lipids, the building blocks of life. Do they assemble into something more? Do they replicate, evolve? We do not know, but we know they could, and that changes everything. Here is why K2-18b matters. For the first few billion years of Earth's history, our planet was nothing like it is now. The atmosphere was toxic, the oceans were acidic, the sun was dimmer, the surface was bombarded by asteroids. Life emerged anyway, not despite the harsh conditions. Because of them, the energy from hydrothermal vents, the chemical reactions in a turbulent ocean, the constant bombardment delivering organic molecules from space. These things did not prevent life. They enabled it. K2-18b has all of these conditions. In fact, it has them in abundance. The radiation from its star drives chemistry in the upper atmosphere. The pressure at the surface creates stable liquid water. The planet's interior heat powers volcanic activity and hydrothermal vents. If life can exist there, it wouldn't be life like us. It wouldn't breathe oxygen. It wouldn't see light the way we do. It might not even have DNA, but it would be life. And that raises a haunting question. If life can arise on a planet as extreme as K2-18b, a world that's simultaneously too hot and too close to its star, a world that shouldn't even have water, then where can't life exist? Maybe life doesn't require a Goldilocks zone. Maybe it just requires any zone where liquid water and energy coexist. And if that's true, then the universe is full of places we never thought to look. Planets orbiting red dwarfs, ice moons orbiting gas giants, rogue planets drifting alone in the dark, warmed only by their own internal heat. All of them could have oceans. All of them could have life. The universe, it turns out, might not be as empty as we thought. There's a concept in philosophy called the Copernican principle. It states that Earth is not special, that we don't occupy a privileged position in the cosmos. First, we learned that Earth isn't the center of the universe. Then, that our sun isn't special. Then, that our galaxy is one of billions. And now, we're learning that our kind of planet, the rocky, temperate, sunlit world, might not be special either. Ocean worlds like K2-18b could be the norm, not the exception. And if life arises wherever conditions allow, then we're not alone. We might not even be typical. Think about that. For all of human history, we've wondered if we're alone in the universe. We've built telescopes, sent probes, listened to the stars for signals. And now, we're finding that the universe might be teeming with worlds where life could exist. Not worlds like ours, but worlds that survive on their own terms. Worlds where fire and water coexist. Worlds that shouldn't be habitable, but are. K2-18b doesn't give us proof of life. Not yet. But it gives us something more important. It gives us possibility. And possibility is where discovery begins. So here's the question we're left with. If life can exist on a planet made of water and fire, a planet that's boiling and drowning at the same time, then what does life actually need? We used to think the answer was narrow, specific, Earth-like. But K2-18b suggests the answer is broader, wilder. Maybe life doesn't need our conditions. Maybe it just needs contradiction, tension, the collision of opposing forces creating something new. Water and fire, chaos and order, destruction and creation. Maybe that's where life thrives. And if that's true, then the next question is obvious. How many planets like K2-18b are out there? How many ocean worlds are we missing because we're only looking for copies of Earth? The James Webb Space Telescope is watching K2-18b right now, capturing more data, searching for more biosignatures. In the next few years, we might know if those oceans are truly lifeless, or if something swims beneath the surface. Until then, we wait. And we wonder. If you want to explore more mysteries like this, the next video on this channel asks an even stranger question. What happens when a star becomes conscious of its own death? Subscribe to explore the universe's impossible stories, starting with the next one. Because K2-18b taught us something important. The universe doesn't follow our rules. It writes its